We will discuss about topic number 12, that is atoms. So in this topic we will discuss atomic models in the beginning, then we will discuss about hydrogen spectrum. So these are the major two topics basically. In atomic models only we will discuss in detail, followed by hydrogen spectrum, and at the end there is a small topic, de Broglie's proof for the you all know that all the elements of the matter are made up of small So if you go to around 150 years back, somewhere in 1890, so that time only people had some idea regarding these atoms, because the experiments like discharge tube or measurement of charge by mass ratio by Thomson, all these experiments proved that there are negative charges inside the nucleus. But same time they know that atoms are electrically neutral. So that means there will be equal number of positive charges also. So now you have a clear idea that there are some negative charges inside the nucleus. Inside the atom there are some positive charges inside the atom. So net charge of the atom is 0. But how these negative charges and positive charges are inside the atom, how the structure of the atom. So to understand that, we need atomic models. So the first person who tried to explain the structure of the atom is J.J. Thomson. He gave Thomson's model somewhere in 1898 to understand the structure of atom. So now if you concentrate on Thomson's model, what Thomson said. So Thomson suggested that inside the atom, there will be a cloud of positive charges if you represent atom in the form of a sphere. And the entire positive charges are inside the spread over the entire region of the atom, and there will be so this is how the atom according to Thomson. So these are negative charges and they are inside the positive charges. So this argument given by Thomson, at that time, according to the practical things what they have observed, this was okay to them. The reason behind this is, so you have studied thermionic emission in the previous class, that is when you heat an atom it emits electrons. So if you see this model also from your birthday cake, so in the similar fashion, it is easy to remove the electron from the cloud of positive charges here. So basically, what practically observed is matches with Thomson's atom model. So that is why at that point of time, people are okay with Thomson's model. But at this point of time, now if you think this model is not valid, the reason is after a few years, another scientist called Leonard, he suggested one more model regarding atom. What he did is he passed an array of cathode rays into a material. So when he bombarded the cathode rays, what he observed is most of the cathode rays passes without any deviation. So what is the meaning of this? If there is a cloud of positive charges, then these cathode rays should hit that positive charges and they should not pass through the atom according to Thomson's model. But Leonard what practically observed is this cathode rays passes without any deviation. So this clearly suggests that there is a lot of empty space inside the atom. So this was Leonard's contribution, that he said the atom, inside the atom there is a huge empty space. Because of that, this cathode rays passes without any deviation. So now there are two models. One model says that inside the atom the positive charges are spread over the entire region and there is negative charges in that. And second model says that there is a lot of empty space inside the atom. So now the people are in a confusion which to follow. To overcome this, one more brilliant scientist is the student of J.J. Thomson. To 1911 to understand more about this ambiguity. So finally he came up with a brilliant model that even now we are following, that is Rutherford alpha particle scattering model, or it is also called Rutherford's atomic model, or it is also called Rutherford's planetary model, because this model almost resembles the planetary model. So the name given planetary model by Rutherford. So what Rutherford did is he bombarded a beam of alpha particles. Alpha particles are the nucleus of helium atom. They contain 2 protons and 2 neutrons. He bombarded this alpha particle into a very, very thin gold foil. And he studied the deflections of the alpha particles. So based on that, he gave some conclusion regarding the atom that gave some clear picture regarding the structure of atom. So we'll study in detail regarding the structure of atom given by Rutherford. Before that, what are the demerits of Thomson's model? That if you discuss. So this scattering, what I said just now, that cannot be explained with the help of J.J. Thomson model. That is the one demerit. It could not explain large angle scattering of alpha particle from metal foils. Second limitation is, we will come across this point later, spectral lines, emission of spectral lines, in fact atomic spectra, that cannot be explained with the help of Thomson's model. So because of these two reasons, no, Thomson's model is not valid now. So based on Leonard's suggestion, now Rutherford constructed a model. That model we are going to concentrate now. The Rutherford's model is clearly explained later by his 2 students. One is Geiger and one more is Marston. So in fact this experiment itself is called scattering experiment. Along with that we will study the conclusions of alpha particle scattering experiment. In this alpha particle scattering experiment, have a source of alpha particles. Imagine this is a source of alpha particle. So one example for source of alpha particle is bismuth. So basically the alpha particle can be emitted from all the radioactive substances, and the energy of the emitted alpha particle is usually from 5 to 7 million electron volt. And the energy emitted from bismuth, alpha particle emitted from bismuth, is around 5.5 million electron volt. So this alpha particle, they will be ejected in all the directions, but we want to make them collimated. We have to make them to move in a straight line. That can be possible with the help of two lead blocks. So this is one lead block, one more lead block. Similarly on this side, one lead block, this side one more lead block. So lead is a very good absorber of particle. Remain those alpha particle which will travel in this, they will be allowed. Only those alpha particles which are traveling in this direction, they will be allowed, and these alpha particle, all these alpha particles will be absorbed by the lead block. So with the help of lead block, we have collimated the alpha particles. Now alpha particles are moving in a straight line. So now these alpha particles are made to hit a very thin gold foil. So this is a support for the gold foil. So this is basically the gold foil. So the gold foil is so thin that there is only one layer of atoms. There is no second layer of atoms present. So this much thin layer is possible only with gold. That is why gold is preferred in this alpha particle scattering experiment. So there is only one layer of gold. So there is no question of alpha particle scattering again. So these alpha particles will hit the gold foil. The scattered alpha particles are detected by a rotatable detector. In fact, this scattered alpha particle, they will hit the zinc sulfide screen, because when this alpha particle hits the zinc sulfide, they produces a light flash. That light flash is detected with the help of a detector. They hit the zinc sulfide screen, they produce the light flash. That light flash is viewed through a microscope, and that is how you detect the scattered alpha particle. Now the question comes, why this is a movable detector? The reason is these alpha particles can scatter in any direction. So in order to detect all the scattered alpha particles, we need a movable detector. So this is the experimental setup by Giger and Marsden. So in this experimental setup, there is a source of alpha particle that emits alpha particle in all the direction. They are collimated with the help of a lead block, and then the collimated beam of alpha particles made to hit a gold foil, they undergo scattering there, and that scattered alpha particles are made to hit a zinc sulfide screen. In that, particles are hitting the gold foil. As Leonard said earlier, there is a huge empty space inside the atom. So what Giger and Marsden observed the same thing. They observed that more than 99% of the alpha particles passes without any deviation. So more than 99% of the alpha particles, they are traveling in their same path. They are not changing their path. That means this clearly says that there is a huge empty space inside the atom. When they moved the detector to observe the remaining scattered light, what they observed is around 14%, no sorry, 0.14% of the particles, they scatter by an angle more than 1 degree. So that means if you have around 100 alpha particles, in that only 1 or 2 particles, alpha particles, they undergo scattering. Remaining 90 plus alpha particles, they passes without any deviation. So this clearly says that the whole mass of the atom is concentrated at the center of the alpha particle. To justify this, they observed the third factor in that is one atom, approximately one atom out of 8,000, 1 out of 8,000 scatter by an angle more than 90 degree. So you know, alpha particle is the nucleus of the helium atom. So that carries positive charge. So now positive charge is moving in this direction. Now see, if this positive charge, if at all it has to scatter somewhat like this by an angle more than 90 degree, then it must experience a large opposition here. So when it experiences a large opposition, then only it can backscatter. So this clearly says that mass is concentrated at the center of the atom. So that will give huge opposition for the alpha particle. So that alpha particle will deviate by an angle more than 90 degree, but remaining alpha particle will pass through the empty space. So this gave the birth to the nucleus of atom. So basically Rutherford discovered the nucleus of the atom. So when you look at the conclusions of Rutherford's atomic model, so first one, more than 99% of the alpha particle passes without any deviation, and only 0.14% of the alpha particles scatter by an angle more than 1 degree, and one alpha particle in around 88,000 alpha particles scatter by an angle more than 90 degree. So these are the conclusions of the Rutherford's alpha particle scattering. So if you draw a graph of number of alpha particle scattered to the scattering angle theta, scattered, and theta is the angle of scattering. So based on the data, if you plot a graph, you'll find that the graph goes like this. So if you carefully observe, you see this region where the scattering is number of atoms is huge. That means huge number of atoms passes without any deviation. If you see this region where the alpha particles are backscattered means they are scattered by an angle more than 90 degree backscatter, they have, the number is very less. So this is a rough graph of alpha particle scattered and scattering angle theta. So now, if I compare the two models. See, this is the model given by Leonard. So there is the positive charges are spread over entire region of the atom, and these are the negative charges inside. And the second model, that is by Rutherford, this is the positive charge and surrounded by electrons. See, this is how electrons revolve around the nucleus. So this region is empty. So this is the model given by J.J. model. Even this model, there are some limitations we'll discuss later. Now see, when alpha particle travels, this experiment goes like this and hits a gold foil, see, gold atom. Only those alpha particle which travel in the line of the nucleus, they will be backscattered. This indicates that the whole mass, more than 95% of the mass of the atom is concentrated at the center of the atom in a small region. So only those alpha particle which travels in that line, they will be backscattered. Remaining atoms, they will be scattered by small angle. So as you move away from the nucleus, they passes without any deviation. So now, to understand more this, we introduce a quantity called impact parameter. So impact parameter is, imagine this is the nucleus and this is the beam of alpha particles. This is the direction of initial velocity of the alpha particle. So this is the dotted line indicates the center of the nucleus. So the perpendicular distance from the center of the nucleus to the initial velocity vector direction is called impact parameter. Impact parameter is the perpendicular distance between the initial velocity of the alpha particle and the center of the nucleus. So if the impact parameter is small, imagine a alpha particle travels like this, then its impact parameter is almost 0. So here the probability of scattering is very high. This alpha particle will backscatter. Suppose if you take this alpha particle which is far away from the center of the nucleus, for this impact parameter is very high, it is represented by B, impact parameter is very high. So this particle will suffer least scattering or no scattering. So impact parameter is high, then the alpha particle is far away from the center of the nucleus, so it cannot deviate. In fact, it is suffering no scattering. But if the impact parameter is small, then it suffers maximum deviation. The possibility of backscattering is there. So that is the importance of impact parameter. So here the angle of scattering will be approximately equal to, I can say, 180 degree. This will undergo scattering like this. That is, for this rays, angle of scattering will be more than 90 degree, but it is less than 180 degree. For this, the particles travel like this. For this, angle of scattering is less than 90 degree, but for these rays, angle of scattering theta equal to 0 degree. So if you see, as impact parameter goes on increases, angle of scattering goes on decreases. So that is the importance of impact parameter. Now see, if you consider here, when alpha particle travels in this direction and it backscatters, but the question comes whether gold foil moves from that point. If you see alpha particle, it contains 2 protons and 2 neutrons. And it has got 4 units of mass, therefore. But if you see gold, the mass number of the gold, that is around 197. So it has got, if you compare with the mass of the alpha particle, this is very, very, very heavy nuclei. So because of that reason, alpha particle cannot move the gold nucleus. Only alpha particle will be backscattered, gold nucleus will remain at rest. Remember that. So deflection is observed only in alpha particle, not in the gold nucleus. Gold nucleus will remain at rest. So these are some important points regarding alpha particle scattering experiment. So alpha particle scattering experiment successfully explains the structure of the atom. Now we have a clear picture how the atom. So the whole mass of the atom is located at the center of the atom by the name nucleus, and electrons revolve around the nucleus. Now the question comes, why electrons are not at rest? So imagine electron is at rest. If electron is at rest, you have studied in electric charges and fields. If there are 2 charges, Q1 and Q2, separated by some distance r, there will be a force exist between them. Its magnitude is 1 by 4 pi epsilon naught Q1 Q2 by r. The famous Coulomb's law. In this, epsilon naught is permittivity of the medium, Q1 and Q2 are the magnitude of both the charges, r is the distance between them. This is the magnitude of the force, and nature of the force depends on the nature of the charges. In fact, if one is positive, other is negative, the force is attractive. If both are positive, force is repulsive. Both are negative, again force is repulsive. You see here the nucleus is positive and electron is negative. So there will be a Coulombic force of attraction between them. Because of that, electron will fall into the nucleus. So because of that reason, electron revolve around the nucleus in circular orbits. So these are some observations of Rutherford's alpha particle scattering experiment. So at that point of time, this was more convincing model, because here also you can easily explain the phenomenon of emission of electrons from the atom. When you supply energy in the form of heat, electrons will be ejected from the atom and no positive charges will be ejected from the atom. But there are some limitations in the Rutherford's atomic model also. So if you concentrate on limitations of Rutherford's atomic model, as I told you in the J.J. Thomson's model, all the materials, they emit radiation of certain wavelengths. We call it as atomic spectra. We have a separate so that was the First limitation of Rutherford's atomic model. It cannot be the atomic spectra emission of radiations from the atom cannot be explained using Rutherford's atomic model. Also, if you take a simplest atom, that is hydrogen 1H1, it contains one proton and one neutron. Such a simple atom shows complex spectrum of particular wavelengths. We call it as hydrogen spectra, that cannot be explained with the help of Rutherford's atomic model. We need Bohr's atomic model to explain that. So that comes next. So that is also another limitation of Rutherford atomic model. Then, as I mentioned, electrons revolving around the nucleus with a particular speed. Now here electrons move in a circular path. If we assume for a particular radius its velocity is constant, that means electrons are exhibiting uniform circular motion. You know, any body which is moving in a circular motion must possess a centripetal force. So this is no longer a uniform motion, it is an accelerated motion. Here the magnitude of speed of the electron may not change, but its direction changes continuously, so it is an accelerated motion. In the course of electromagnetism that you study first, electromagnetic waves. In that you will see that the source of electromagnetic wave is accelerated charges. That means accelerated charges emit energy in the form of electromagnetic radiation. Look at the electron here. The electron is revolving around the nucleus. So it is the accelerated motion of the electron. So it has to emit the energy. As it emits the energy, it loses energy. So slowly it tends to. So this also one of the drawback of Rutherford's atomic model. So the three drawbacks of Rutherford's atomic model. One is it could not explain why atoms emit light of only discrete wavelengths, and it explain the why electron in the orbit cannot emit electromagnetic radiation. So these are some drawbacks of Rutherford's alpha particle scattering model. Students, in your study material, go to atoms in that introduction part, that is J.J. Thomson's atom model. It is also called Plum-Pudding model, and its limitations are given, followed by Rutherford's nuclear model is given, and its limitations are also given there. Then in detail, Marsden and Geiger experiment, alpha particle scattering experiment is given. Its analysis, that is conclusion part, is also given, and explanation for that is given. Just go through till that conclusion part. Geiger-Marsden alpha particle scattering experiment and its conclusion part, till that graph. Go through that. So dear students, one more point here you need to remember is distance of closest approach. So here is the alpha particle, the nucleus. Now imagine this alpha particle and nucleus are at infinite separation. When the distance becomes infinity, there is no interaction between alpha particle and the nucleus. When there is no interaction, there is no force between them. Now, if you push this alpha particle by giving some kinetic energy to the alpha particle, now alpha particle begin to move towards the nucleus. You know, alpha particle is positive in nature. This nucleus is also positive in nature. You know, now this is also a positive charge, this is also a positive charge. There will be a force of repulsion between them. So that means someone is opposing alpha particle. Who is that? The nucleus. Nucleus is opposing the motion of the alpha particle towards the nucleus. So that means if alpha particle has to reach the nucleus, then it has to do some work. If it has to do some work, that will be at the cost of the kinetic energy. So as alpha particle moves towards the nucleus, its kinetic energy goes on decreases. Why kinetic energy goes on decreases? It has to do work to overcome the Coulombic force of repulsion. So now the question comes, what work that alpha particle does? Is it recoverable or it is lost? It depends on what? It depends on whether that Coulombic force is a conservative force or non-conservative force. If it is a non-conservative force, whatever work done, that will be wasted. You will not get it. If it is a conservative force, you will get that. Coulombic force, as you know, or you will study in the first topic, it is always a conservative force. So what work alpha particle does is not dissipated, it will be stored as potential energy of the alpha particle nucleus system. So as alpha particle moves towards the nucleus, slowly kinetic energy is converted into potential energy. So now alpha particles comes closer to the nucleus. Somewhere when it reaches when it is at a distance of r0 from the nucleus, its potential energy, kinetic energy becomes zero and potential energy becomes maximum. So once its kinetic energy is zero, it cannot travel further distance. So this distance between alpha particle and the nucleus is called distance of closest approach. So what is the distance of closest approach? The least distance from the nucleus at which an energetic alpha particle traveling towards the nucleus stops. And after that, what happens? There is a closest approach. So now if you calculate the distance of closest approach, you can find the size of the nucleus. This is how Rutherford came to know about size of the nucleus. Now at this point, the entire kinetic energy is converted into potential energy. How to calculate the potential energy? So at point P, kinetic energy is equal to potential energy. The question comes, how to calculate the potential energy? Imagine there are two charges, one is Q1 and one more is Q2, separated by distance of r. This is a simplest two-part charge particle system. The potential energy of this system, magnitude of one charge, so into you can write potential of the other charge, or you can write directly U equal to 1 by 4 pi epsilon naught Q1 Q2 by separation between them is R. So this you will study in the second topic, that is electrostatic potential and capacitors. That in that chapter you will study potential energy of two particle system is 1 by 4 pi epsilon naught Q1 Q2 by R. So now Q1 is positive, Q2 is positive, then potential energy of that system is positive. Q1 is negative, Q2 is positive, potential energy of that system is negative. Q2 is negative, Q1 is positive, again the potential energy is negative, both are negative, potential energy is positive. Now the question comes, what is the meaning of potential energy negative? What is the meaning of potential energy positive? Now you take the first case where both the charges are positive. When both the charges are positive, the potential energy is positive. You look at the force. The force between those two charges will combine those two charges or will move them, will try to separate them. If both are positive or both are negative, then force between them is repulsive. When the force between them is repulsive, the charges move away. That means the force is trying to separate those two systems. That means it is no longer a bound system. So potential energy is positive, means it is no longer a bound system. Then if one charge is positive and another charge is negative, then potential energy between those two, the potential of the system is negative. What is the meaning of that? The force between them is attractive because one is positive, one is negative. So that means it is a bound system. What is the meaning of bound system? You need to exert some force to separate those two charges. It is true in the case of atoms. Now here, if you look at the potential energy, what is the potential energy here? 1 by 4 pi epsilon naught. What about first charge? That is alpha particle, that is Ze, and not Ze, that is 2e, because charge of alpha particle is 2e. And what is the charge of the nucleus? Ze divided by V square. Now here potential energy is positive, that is why this is no longer a bound system. Here, after reaching here, the alpha particle will retrace its path. Now I am into epsilon naught into Ek. Ek stands for kinetic energy provided to the alpha particle. So this is the distance of closest approach. Now, in the alpha particle scattering experiment, Rutherford measured the distance of closest approach, and that is of the order of 10 to the power minus 14 meter. Now, when he measured the distance of closest approach as 10 to the power minus 14, now you think in the Rutherford's point of view, what may be the size of the nucleus? So size of the nucleus should be less than that. On that basis, he said size of the nucleus is of the order of Fermis. What is Fermi? 1 Fermi equal to 10 to the power minus 15 meter. You got the size of the nucleus, that is around 10 to the power minus 15 meters, of the order of 10 to the power minus 15 meter. This is how he found the size of the nucleus using distance of closest approach. This is very important concept, distance of closest approach. We will solve one or two problems based on this later. Just go through this distance of closest approach. So now you see, this is the nucleus, and imagine you bombard a beam of alpha particle. See, this particle here, initially the alpha particle is moving in this direction. Now it will go to a particular distance, and that is distance of closest approach, then it will bounce back. But if you see this particle, see here there is one charge, that is nucleus, and here is alpha particle. So this is a separation between them. So you know, in the definition of Coulomb's law, you have studied the force between 2 point charges will be along the line joining the two charges. So this is the line of action of force. In this direction force will be there. When the alpha particle comes here, this will be the direction of force. Alpha particle comes here, this will be the direction of force. Alpha particle comes here, this will be the direction of force. Alpha particle comes here, this will be the direction of force. And because of that, it will be pushed outward everywhere. That is why alpha particle travels like this. So basically the trajectory of the alpha particle is determined by two laws of physics. One is Coulomb's law and second one is Newton's second law. Net force is mass times acceleration. So here net force is nothing but Coulomb's force of repulsion only. So here also this charge will pushed outward, here also 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 pushed outward. So the charge goes like this. Here the charge goes like this. When it is far away, there is no deflection, charge goes like this. If you look at here the force is in this direction. So force is opposing the alpha particle to come closer to the nucleus. That is why at one point alpha particle stops and comes back. So the deviation in the path of the alpha particle can be understood with the help of Coulomb's law as well as Newton's second law. So this important points is given in page number 93. So in the you have gone up to conclusions of alpha particle. After that explanation part is there. Just go through that and note points 1 and 2. Go through that, and below that impact parameter we have discussed that time. That is also there. Below that distance of closest approach is there. So just go through these points. So dear students, using Rutherford model, we got a clear picture of atom. Also we got size of the atom, and we got clear picture of Leonard's suggestions regarding empty space inside the atom. See, if you look at the size of the atom, that will be around 10 to the power minus 10 meter. Size of the nucleus is 10 to the power minus 15 meter. So that means atom is around 10 to the power 5 times larger than the nucleus. So this gives you a clear proof that 90% of the atom, more than 90% of the atom is empty space. If you believe that you are made up of atoms, position of electron to the position of nucleus. In addition to these points, Rutherford also derived expression for total energy of an electron in terms of its radius in hydrogen atom. So that is the derivation of expression for total energy of an electron in terms of radius. Now see, let's start in a new page. This is revolving electron and this is nucleus. So I told in the beginning itself, electron is exhibiting uniform circular motion here. So any body which moves in a circular motion must possess a centripetal force. Now you tell me, centripetal force is a fundamental force. Just like when you have two masses separated by some distance, gravitational force between them, or two charges separated by some distance, electrostatic force between them. No, centripetal force will not come magically. Some other force must behave like centripetal force. So if you take motion of the earth around the sun, the gravitational force of attraction between sun and earth acts like centripetal force. Motion of the moon around the earth, the gravitational pull of the earth acts like centripetal force. Similarly, when an electron is revolving around the nucleus, who acts like centripetal force? No doubt it is the Coulombic force. So Coulombic force of attraction behaves like centripetal force. So Fe is equal to Fc. You know the general expression for centripetal force. What is the general expression for centripetal force? mv square by r. Do you know what is the expression for Coulombic force? Yes, 1 by 4 pi epsilon naught q1 q2 by r square. R is the distance from electron to the nucleus. So that is r square. Now what is Q1? Q1 is charge of the electron, E. And you are deriving this relation for which atom? Hydrogen atom. The nucleus of the hydrogen atom consisting of what? One proton and one neutron. Whether neutron carry any charge? No, only proton carry charge. And what is the charge of the proton? It is equivalent to charge of electron only in magnitude. So it is E into E by r square. So square by r. So our basic intention is to calculate the total energy of the revolving electron. So that means you need to calculate its kinetic energy, also you need to calculate potential. They need to add to get the square, which is equal to E square by 8 pi epsilon naught r. Let it be equation number 1. So that is the kinetic energy of the revolving electron. Now, we need to calculate potential energy of the revolving electron. Or we need to calculate the potential energy of the electron. How to calculate the potential energy of the electron? So, this comes in the second topic, as I told you, and you need to find out the potential energy between them. Then U equal to magnitude of one charge into electrostatic potential due to other charge. So that is Q1 into the potential due to other charge is 1 by 4 pi epsilon naught Q2 by at what point Q1 is located, that is R. So which is equal to 1 by 4 pi epsilon naught Q1 Q2 by R. This formula only I have written few minutes before directly. And here I have told you all the conditions. What is the meaning of negative potential energy? What is the meaning of positive potential energy? So now come to the electron nucleus system. Now here magnitude Q1 is minus E. Remember, when you are writing the Coulombic force, you did not consider the sign of the electron, because there if the charges are like, the force will repel each other, means the direction of the force is away, and if the one charge is negative, then force is attractive. That attractive or repulsive, that itself will consider, that itself gives the significance of sign. If both are negative, repulsive, both are positive, repulsive, one is positive, one is negative, attractive, that itself gives the significance of sign. But here it is potential energy. We are discussing about a scalar quantity. So you have to put minus E, not only E, into what is the potential due to nucleus, that is 1 by 4 pi epsilon naught into what is the charge E and at what distance R. So what is the potential energy? Minus E square by 4 pi epsilon naught R. Equation 2. So we got expression for kinetic energy, we got expression for potential energy. Now we need to calculate the total energy. How to calculate the total energy? Very simple. Total energy E equal to sum of kinetic energy plus potential energy. What is kinetic energy? E square by 8 pi epsilon naught R plus what is potential energy? Minus E square by 4 pi epsilon naught R. So that means total energy equal to, what is the answer you are getting? E square by minus E square by 8 pi epsilon naught R. So this is the expression for total energy. So expression for total energy of the electron in the orbit is minus E square by 8 pi epsilon naught R. What is the significance of total energy negative? Already I have told you the significance of negative energy. What is that? It is a bound system. So if you want to make electron free from the nucleus, you have to supply some energy. And what is the amount of that energy? That is minus E square by 8 pi epsilon naught. When you supply this much amount of energy, you can remove an electron from the orbit of the atom. So this clearly says that when you supply heat, the thermionic emission, what you have studied, no? When you supply heat, electron gain energy and they come out of the atom. This is what practically observed. So Rutherford gave a clear picture of that with the help of his model. Also, he gave the expression for radius and velocity of the electron orbit. So before that, we'll discuss that radius as well as velocity. So mv square equal to, from the v square by r equal to 1 by 4 pi epsilon naught r square, 1 r square will cancel. So from this you will get mv square equal to e square by 4 pi epsilon naught r. So I need the expression for radius. So what is the radius of the electron? E square by 4 pi epsilon naught mv square. So that is the expression for radius of the electron. As I mentioned, you can find the expression for velocity also from this. So velocity of the electron is equal to, you have to take square root of, you have to bring m here and then you take the square root of that, e by root of 4 pi epsilon naught mr. So that is the expression for velocity of the electron in its orbit. So these are the ideas given by Rutherford. He gave the structure of the atom. Also he gave the energy of the electron in the orbit. Also give the expression for radius and velocity of the electron in the orbit. So just go through that. It is in page number 95 in your study material. Expression as well as below note points, note point 1, 2 and 3. So in note point 1 they have given what happens if the total energy is positive. I already told you, if the total energy is positive, it is no longer a bound system. In that case, electron cannot revolve around the nucleus. Electron will move to infinity. Since the total energy is negative, electron is bound to the nucleus and it is revolving around the nucleus. Just go through that derivation. problem in this. This is not the problem from problem sheet or the problems which is given at the end of the question, end of the chapter. It's an additional problem. So in a Geiger-Marsden experiment, what is the distance of closest approach to the nucleus of a 7.7 million electron volt alpha particle before it comes momentarily to rest and reverses its direction? So the question is simple. You need to find out the distance of closest approach. So directly we can write the formula and we can substitute. What is the formula for distance of closest approach? R naught equal to 1 by 4 pi epsilon naught into 2 ZE square divided by EK. So which is equal to, this 1 by 4 pi epsilon naught. If electric charges and fields are over for you, then you can remember this value, 9 into 10 to the power 9. So 9 into 10 to the power 9 into 2 times E square, that is 1.6 into 10 to the power because the million electron volt. Whether electron volt is a SI unit of energy? No, it is joules. So we have to convert into joules, multiply by 1.6 into 10 to the power minus 90. So when you do this, this 1.6 10 to the power minus 19 will cancel. So when you calculate this, this is 10 to the power 6, goes to numerator, 10 to the power minus 25, minus 25 plus 9 will come, plus minus 16, then 9 into 2 is 18, 18 into 1.6 divided by 7.7 will come approximately 3.84 into 10 to the power minus 16 Z meter. So if you continue in this problem, that is if you take gold, then for gold Z is equal to 79. So then R naught becomes 3.84 into 79. That will come approximately 3 into 10 to the power minus 14 meter, or approximately equal to 30 Fermi. So if you see the radius of the gold nuclei, which is practically observed. So practically observed radius of the gold nuclei is around 6 Fermi. What is the distance of closest approach? 30 Fermi. So 30 Fermi is much larger compared to 6 Fermi. What is the meaning of that? The meaning of that is alpha particle comes along its way and it is not touching the gold nucleus. In fact, little bit far away from the gold nucleus, it reverses its direction. So this clearly says that size of the nucleus is much smaller than distance of closest approach. So remember, very good problem to understand distance of closest approach. Copy that. So there is one more problem regarding that energy expression. It is found experimentally that 13.6 electron volt energy is required to separate a hydrogen atom into a proton and electron. What is the meaning of that? That is the total energy of the electron revolving around the nucleus. So if you supply that much amount of energy, electron becomes a free electron. Their question is compute the orbital radius and velocity of the electron in a hydrogen atom. So a few minutes before we have discussed energy of the electron in the hydrogen atom in detail. So this problem you just copy and you have to try your own. So in the next class anyhow I will do this. But before that you have to give it a try and you must get the answer. So tomorrow you have to just cross verify the answer. Total energy is given. They are asking you to calculate the orbital radius and velocity of the electron. So you know the expression for total energy, E square minus E square by 8 pi epsilon naught r. From that you can easily calculate the radius and then you have to calculate the velocity. Just copy the problem and you need to work out. So the points we have discussed in today's class is we started with the Plum-Punting model given by J.J. Thomson. Then we found that this model is not an appropriate model to explain the structure of atom. So then Leonard gave some very important suggestions regarding the empty space inside the atom. Based on that, Rutherford did experiment, gold foil experiment to study the structure of the atom. Later his students Giger and Marsden performed experiment in detail and they gave Rutherford's alpha particle scattering experiment. In that we got a picture of structure of atom, that most part of the atom is located the center part of the atom in the form of nucleus and electron in circular orbits. From that we have also calculated the energy of the electron and we have also calculated velocity of the electron and radius of the electron orbit. And the conclusions of Rutherford's alpha particle scattering important. The demerits of Rutherford's alpha particle scattering, that is also important. And energy of the alpha partners, energy of the electron in the orbit, that is also sometimes appeared in the exam. So if you look at the first demerit of the Rutherford's alpha particles scattering, that is, it couldn't explain the spectral lines. So regarding that, we have to discuss, that is atomic spectra. So what is atomic spectra? And then we have to discuss Bohr's atomic model. With the help of Bohr's atomic model, we need to discuss hydrogen spectrum. So just go through whatever discussed in today's class. If you have any doubts, you can use doubts portal. Solve that problem before you